Okay, today we're going to be talking about moment of inertia, what it means, and how to derive the moment of inertia for some common mass distributions. Moment of inertia, or rotational inertia, is a physical quantity that represents an object's tendency to resist angular acceleration. So in other words, the greater an object's moment of inertia, the greater the torque required to cause it to accelerate rotationally. So you should be thinking, I feel that sounds familiar. Where did I see this before? So if you were thinking that, then you're right. You have seen something like this before, and it does look familiar. It's because mass and moment of inertia are counterparts to one another. Mass is the linear counterpart of moment of inertia, and moment of inertia is the angular or rotational counterpart of mass. In the same way that we have Newton's second law in the linear sense with forces, we now also have a Newton's second law in the rotational sense with torques. One thing to keep in mind, however, is that there are some limitations to this linear and rotational analog. It's important to note that 150 pound force only results in one acceleration when exerted on one certain mass. The same 50 pound force is going to result in a smaller acceleration on a larger mass. Torque, however, is the cross product of the lever arm and the force. So in order to cause a certain angular acceleration for an object or moment, you could either increase the force applied or increase the lever arm in order to create a certain angular acceleration. So this is why wrenches are handy and why wrenches with a pipe to extend the handle are even handier. So from our Newton's second law lab for torques and soup can races, we have some idea that moment of inertia is related to mass as well as the distance that particular mass is from the axis that it rotates around. It turns out that the moment of inertia for a system of masses is given by this equation here, where you have to take the sum of each mass times the square of the distance from that mass to the axis in which it rotates about, and you sum it over every mass in that system. This is the equation that we use for discrete mass distributions. And discrete mass distribution is just a fancy way of saying point masses. So consider this mass distribution that consists of two masses, M1 and M2, at distances R1 and R2 respectively, rotating about this axis given here that's vertical. You can apply the equation for moment of inertia for a discrete mass distribution by taking the sum of these two products, M1 R1 squared plus M2 R2 squared. Something like this would be a reasonable way to model the moment of inertia of two planets orbiting around a star, for example. But what about something like this? If we took a bunch of these masses, what would happen? We would have to go down the line and do the same thing for as many particles of mass we have. And to do this in terms of an actual rod for discrete masses would be really hard. Fortunately, in cases like these where the mass distributions are what we say continuous, which is just a fancy way of saying actual shapes rather than dots or points, we have the integral form of the moment of inertia equation, which is given here to the right. One thing to note here is that there is one way, correct way to do an integral, and there are an infinite number of ways to incorrectly evaluate an integral. So here's one of the many ways that you can evaluate this wrong, but you don't want to integrate over the differential dm from 0 to m. That's one thing you'll see often. is integrating from 0 to m, and then just saying, oh, that's easy, so this just ends up being mr squared. Now, there are a few problems with this, and the fact is that if this object is said to be uniform, that means that its mass is distributed evenly throughout its shape. So you don't want to do that because it implies first that everything of mass m would have the same moment of inertia as anything else with the same mass. And we know that can't be right because we know that things rotate differently under the same conditions. Secondly, integrating from 0 to m implies there are some places where there is less, even 0, or more mass than other places. And that completely goes against what a problem would say where the mass is uniform. So now you're probably thinking, well, how do we integrate this then? And the answer here is it depends on the shape of the mass distribution we're talking about. In the following slides, we'll integrate some common shapes that you'll see. For our first example, we've got a rod of uniform mass density that's rotating about its center. So you can think of someone twirling a baton while holding the baton at its midpoint. Before we begin, we need to first take note of the fact that there's a mass m, which we'll use capital, that's distributed evenly throughout the whole length of this rod. Now, for these integrations, it's important to note that for our mass distributions, there are small masses called mass elements in our shapes that comprise the whole object. Now, in this example, this small mass element has a very, very small length of dr. And if the mass is distributed uniformly, we're able to set these two ratios equal to each other. Here we're going to solve for the mass element dm, and we're going to end up substituting this into our integral. So when we substitute, we get something that looks like this. And since big M and big L are constants, we're just going to pull them out of our integral, which leaves us with that. Now, for a rod of length L that's rotating about an axis that goes through its center, we should note that on one end is negative L over 2, and the other end is L over 2 positive. So those are the limits of our integration. So performing this integration, we get m over L r to the third over 3, which needs to be evaluated from negative L over 2 to positive L over 2. Keep in mind that since this is what math teachers would call a definite integral, that we don't get a constant at the end. So let's finish wrapping up this integral. We now plug in L over 2 to the third over 3 minus the lower limit to the third over 3. And when you simplify that, it will end up coming out to I is equal to 1/2 mL squared, which is the moment of inertia for a rod that is rotating about an axis that goes through its center of mass. For next derivation, we're going to be doing the moment of inertia for the same uniform rod, except it's going to be rotating about an axis that goes through one of its ends perpendicular to the rod itself. Now, luckily, since we're talking about the same rod with the same mass distribution, we could still do this move where we say the whole mass of the rod over its whole length is equal to a very tiny piece of mass over a very tiny length of the rod. Now, when I like to think about this, I think of how if you were to make a mixture of Kool-Aid, one sip of a full glass is going to taste exactly the same as the whole glass itself, or even a bigger piece of that. Because if it's mixed perfectly and if it's perfectly uniform, then you can say that those ratios are pretty much the same. Now, when we substitute into our integral like before, you'll notice that it does end up being the same to begin with. So we still have our big M over big L and our differential dr, and we can pull out that big M and that over big L, and we're still left with this. However, we have to remember that the axis is located differently, and for that reason, we now have to integrate over different limits. So here, we're going to start at the limit of 0 and go all the way to a full capital L. So those are our limits of integration. Now, while the integral itself looks the same, because it still comes out to our r cubed over 3, we're evaluating it differently. So I'll show a little bit more work on this one. I'm going to pull out that 1/3. We still have our big M over big L here, but we're doing times L cubed minus 0 cubed. And after we clean all this up, what we see is that we end up with the moment of inertia is equal to 1/3 mL squared. So notice that the moment of inertia of a rod when the axis of rotation was through the center, we had a coefficient of 1/12, and this time we have a coefficient of 1/3. So the moral of this one is that where the axis of rotation is matters a lot. So mathematically, the reason why the location of the axis of rotation matters is because each of our mass elements were located different places with respect to the axis of rotation. So when we did our integral, yes, we did talk about the same mass elements, right? However, in one integral, we had to evaluate that integral from the limits of 0 to L, whereas the other, where it was rotating about its center point, we're able to integrate from negative L over 2 to positive L over 2. Now, the fact that our integration limits were different is going to totally affect how the rest of the integration plays out, which in turn is going to result in a different moment of inertia. In our next derivation, we'll be talking about how to find the moment of inertia for a hoop rotating about its symmetry axis. So think something like a hula hoop being rolled on the ground. So notice that this is kind of a rod that's just bent into a circle shape. We can actually use this to our advantage by thinking of this in polar coordinates, as opposed to our usual Cartesian x, y, z coordinates. This will make more sense when we define our mass element dm. So let's just take a look at this hoop a little differently so that we're staring right down its symmetry axis. In this example, we're going to have to define our mass element dm. Very similar to the Kool-Aid analogy, but this time instead of integrating over a straight length, we're going to integrate over an angle theta. So here's our theta. We're defining it from the horizontal, and notice that our theta will swoop and it points at all of our little dm's. And our dm's are also the same distance away from the axis of rotation, which is, just the radius. So it's a little different than saying the leftmost dm is located at 0 and the rightmost dm is located at plus L. In this case, the mass elements which make up our big M, are located at different thetas measured from 0 radians or the positive x direction. So we're interested in a mass element in terms of theta. Here, the total mass is located by sweeping through the full angle of 2 pi radians. And this is equal to the ratio of dm to d theta. Like a small dm is a small angle wide. Now, we can solve for dm to set up our integral, which gives us dm is equal to big M over 2 pi times our differential d theta. So now let's just plug this into our integral and see what happens. So we keep our r squared, and our dm gets replaced by this term here, which I brought over on the bottom left. And it looks like we've actually lucked out here because now our r is actually constant. So we can actually upgrade in a way our r squared into capital R squared, and that can get pulled out. Also, our big M and our 2 pi get pulled out. And we have a nice integral to do here where it's just our differential d theta. And now our limits of integration are from 0 to 2 pi because we have to sweep throughout the whole circle. So our next line in this integral ends up being just 2 pi minus 0. And the 0 doesn't bring anything to the party. You'll notice that our 2 pi cancels. So now we're left with just our moment of inertia being equal to m r squared. And that's the moment of inertia for a hoop where its axis of rotation is through its symmetry axis. So the moral of this one is that you don't always have to integrate over lengths. You can also integrate through angles, which is especially useful for curved shapes like this. So sometimes, while we may not be used to it, it's more beneficial to do our work in polar coordinates because, honestly, I would not want to integrate over the shape in our XYZ Cartesian coordinates. That would be extremely unpleasant. So it's actually clever to integrate this way. It will make your life a lot easier. For our next one, we have a hoop rotating about an axis in line with its diameter. So think of a hula hoop again, but this time it's being spun around like a coin. Here we're going to actually call this r prime for the integral. So we're going to get a prime in there. And the moral of this one is an important one. It's to remind you that r is actually a distance away from the axis of rotation. So right off the bat, before we go about solving for our mass element dm, we first need to take note of what's happening here with our r. So again, remember that we're talking about this distance, this perpendicular distance from our dm to the axis of rotation. The problem is that as we go through the shape, these r's get really small and then get to the largest that they will be and then go back small again. So that's going to be extremely hard to integrate unless we come up with a substitution. So our strategy in this one is we want to think about a way that we can actually exploit the fact that a circle is symmetrical about its center. So we want to somehow work our theta in here. And the only way we can really do that is to try to imagine this imaginary line here called r prime is the adjacent side to a triangle that has a hypotenuse of our regular r, where our angle is defined as such here. Our first substitution has to involve swapping out our r prime, which again is measured from our axis of rotation, and we want to express in terms of theta, which exploits the fact that we've got a nice circle to work with. So here, r prime is really big R cosine theta from right triangle trigonometry. Now, our other substitution that we're going to be using is the same as before. The whole mass of the ring is distributed over a full 2 pi sweep across the circle. And that's equal to this proportion of our mass element over our small angle theta. So our dm is actually pretty much the same as before. So just rounding everything up, we're going to do two substitutions. Our first one is here, and that pretty much addresses the fact that our r prime changes as you go down this hoop. It swaps out our r prime, which is difficult to deal with a theta. So we can pretty much locate our mass elements, dm, and pretty much look their address up based on theta. So if we were talking about finding the mass elements, here at 3 o'clock, theta equals 0, 2 pi. If we're talking about 12 o'clock, theta is equal to pi over 2 radians. If we're talking about the 9 o'clock dm, then that one is pi. And this one is located at 3 pi over 2. So that's how you want to think of it. The second one, a little easier. This just has to do with our mass element. So let's start plugging everything that we know in. Here, we're going to substitute. First, we're going to swap out our r primes. So we get r squared cosine squared theta, and our mass element ends up being m over 2 pi d theta. All right, so I'm going to pull out all of our constants, which gives us our m, our big R squared, our 2 pi can come out, and we are left with a cosine squared theta d theta. Now, in terms of our limits, we're still imagining this 0 here. We need to swoop around this whole circle, so our limits are the same as before. 0 to 2 pi is where we're integrating this this theta integral. Now, I'm not gonna lie, I'm a little rusty with all the integration techniques, and I kind of depend on integral tables, so I'm going to trust that you know how to do the substitution. I believe it's a U substitution to integrate cosine squared theta. It does come out to theta over 2 plus sine 2 theta over 4. And we have to evaluate from 0 to 2 pi. So when we plug everything in, we do have our mr squared over 2 pi. And we get two terms here. So first, our term is 2 pi over 2 plus 0. And we're going to subtract that from plugging 0 in, which just goes 0 minus 0. And we are given this moment of inertia as 1/2 mr squared. For our next moment of inertia derivation, we're going to be talking about the moment of inertia of a disk that's rotating about an axis through its symmetry axis. So essentially, if you were to think about an actual coin rather than a hula hoop rolling on its edge, that would account for a disk. Now this time, our circle is now full of mass. And the moral of this one is to just show you that we can also deal with areas in the same way that we dealt with lines. For our mass element in this case, I've shown it in red here. It's a little larger than it should, but just so you can see, we need to start by thinking about how much mass we have and over what space. So here, as always, our mass is still big M. That's the mass of the whole disk. And it's spread out over an area of pi capital R squared. Just like the Kool-Aid thing, our fraction in the side of the equal sign is our usual dm over, this time, d area. But this time we're actually going to write it as dr times r d theta. So let me explain where that comes from. Let me just redraw this mass element here, which this time is actually kind of like a piece of this wedge here that you can see. And we're making an approximation. Essentially, we're arguing that even though that you see these curves, we're arguing that this is a rectangle. And as such, we're approximating so that all we have to do is figure out the base times the height, or length times the width. For a small mass element, this is going to go dr on one side, and this arc length here is given as r d theta. Now, just as a reminder, this comes from the fact that in our kinematics unit, we talked about how to find an arc length, and that was just r times theta. So it's essentially the same idea here, except we're talking about a set r and a differential d theta. So as you can imagine, our mass element is going to look a little scary. Once we get dm by itself, we have our big M over pi big R squared times dr and r d theta. All right, so let's substitute our mass element into our integral. Here we've got the integral of r squared, and replacing for our mass element dm, we've got the expression we've got from the last slide, big M over pi r squared, big M big R, dr. Now there's another differential term here, d theta times r. Now because of that, we will have to integrate twice. One integral will be for dr, the other is for d theta. So at this point, I'm just going to pull out everything that's a constant. We've got our big M over pi big R squared. And we've got one integrand and a second integrand for dr and d theta. Now we will have to integrate over all of the area of the disk. So that means that when we integrate over the differential dr, we have to go from 0 to big R, the whole amount. Likewise, when you think about what angle we have to swoop through, we have to swoop from 0 to 2 pi. Now, if we like, we can separate the integrals. That is allowed, just to make our work a little neater. So here's our integral with respect to r, and then our integral with respect to theta. So here our integrals are not too bad. Our first one for the r differential ends up being r to the 4th over 4, evaluated from 0 to r, times the other integral, which will end up being just theta, evaluated from 0 to 2 pi. Now, when you evaluate those at the limits, we end up with this term, which is I is equal to 1/2 big M times big R squared. So there's your moment of inertia for a disk. So our final moment of inertia derivation that we're going to do for this video is a solid sphere. Now, the mass element for this one, you want to think of as we're approximating it as kind of like a cube of a watermelon, which is not exactly like a cube, if you know what I mean. But here I made it a little larger so you could see. But this is a 3D integration, so as you can expect, there's going to be 3 integrals involved. So let's take a look at that mass element. Now for this mass element, we're still doing the same thing as we've been doing before, except now we're taking the whole mass of the sphere over the whole volume rather than a length or an area. Now, this works out for us because we know the volume of the sphere is 4/3 pi the whole r cubed. But when you think of the differential and the mass element that comes with it, we have to consider the edges of this so-called cube. And it's going to start off similar to our disk mass element. So we do have this dr here, which radiates away from the center. And we have our r d theta, which showed up here. Okay, now the new thing is that in spherical coordinates, there's actually another angle that you could sweep through. We call that the angle phi, and it's measured like this. So there's phi. Now our third dimension is actually r sine theta d theta, and it's obtained similarly from our r d theta, except there's like an extra step there. Now, if you just look at that for a while, hopefully it would make sense, but if not, we can talk about it more in class. But for now, we'll just have to accept the fact that this differential here has 3 integrals that we're going to have to perform. And when you mush all of that together, it's r squared sine theta dr d theta d phi. So now, like before, I'm just going to pay attention to the middle term and the rightmost term. And that's going to get us our mass element. Solving for dm, we get big M over 4/3 pi big R cubed times r squared sine theta dr d theta d phi. There's our mass element that we're going to substitute into our integral. Now, before we get too deep into this integral, we have to note that this is actually another situation where there is an r prime here. And what I mean by that is going back to the hoop example, where we had our hoop here, and this time our axis of rotation went through one of its diameters. We have to do a similar step here because our mass element that time was dependent on where you are in the hoop. And the problem here was that this value here, r prime, was always different. So if you rewind back to that hoop example, we actually have to say that another substitution is going down where r prime is equal to r sine theta. So not only are we subbing in for this mass element here, we also have to substitute out that r prime. And once we do that, we will end up getting something that looks kind of scary. Here, our integral becomes 3 now. And our r prime squared will just end up being r squared sine squared theta. And from our mass element, we've got, first let's go with the full mass over the full volume, big R cubed, times our r squared sine theta, and then our differentials dr, d theta, and d phi. So let's tidy everything up just by pulling all our constants up front and combining like terms. Here I can pull out my total mass over total volume, 4/3 pi big R cubed. I can't pull anything else out. And we've got an integral for r. At this point, we've got r to the 4th dr. We've also got an integral for theta. And this time we actually get sine to the 3rd power d theta. And now we've got an easy integral for phi. Now, figuring out our limits is an interesting case. So here, let's say we've got our axis here, just like in the picture to the upper left, and here we've got the center of the sphere. The way I like to think about this is that when we integrate for the whole volume of the sphere, we have to first sweep from 0 to the max radius of the sphere. So we're building up this radius. So we know that our integration has to go from 0 to the full amount of radius. And theta is opening this up. So we're sweeping from 0 to half a circle, right? So imagine like opening up one of those fans. Okay, now from the side point of view is where I'm drawing this next picture. So like now we can't really see our fan, but we have to swoop that fan the whole 2 pi. And once we do that, we'll have swept over the whole volume of the sphere, if that makes sense. So that's how we establish our integration limits. So now continuing on with this integral, we've got our coefficient that represents the total mass over the total volume. And I'm going to go ahead and evaluate the first and the last integral. This will give us an r to the 5th over 5 after you evaluate it from 0 to r. And our final integral is an easy one. That's just d phi integrated from 0 to 2 pi. So that will end up just being 2 pi. Now the one in the middle for theta is the annoying one, and I'm not going to lie, I'm using an integral table here. But this one is going to be cosine cube theta over 3 minus cosine theta. Now that we still need to evaluate from 0 to pi. Okay? So I'm gonna combine everything. And if you're following along, after you simplify everything, so you plug in pi for theta, make sure your calculator's in, the appropriate mode. Here, we do end up getting something like this. 6 over 20, big M, r squared over 4 over 3. And then combining everything even further, we got 2/5 big M times big R squared for the moment of inertia of a sphere rotating about an axis that goes through its center. And there you go. Several derivations for moment of inertias of different mass distributions. I hope this helped you understand how to set up these integrals a little better. I personally think that if you want to get good at this for your class, that you should rewind this a few times and make sure that you can follow along with each step and that everything makes sense. And these are the most common shapes that I've seen in preparing for AP physics exam, looking at old exams. So it would be good if you can, not only recall these ones, but understand at least how the integrations are set up and be familiar with what terms you might encounter in these calculations. All right, so thanks a lot for checking in, and I'll see you in class.